So here's the agenda for today, two 45-minute sessions. The first session will be kind of learning the basics of Spark, using DataFrames and SQL, doing a bit of time in data analysis, learning about how to use memory in Spark and some Spark internals. I would like to use the second 45 minutes to give you the opportunity to actually download one of the 400 data sets and do something with it. There's a bunch of people here from Databricks who can help out as TAs. I might also use the second half to kind of wrap up anything I wasn't able to get to in the beginning. Okay, so I was thinking a lot about what data set to use, and I found that actually maybe a timely thing to do would be to look at the 4th of July calls to 911 that happened like 2 days ago, specifically requesting the San Francisco Fire Department. So that's kind of what we'll kind of be doing and exploring a couple of data sets around this. So another thing you might want to do right away is go to this link, data.sfgov.org. And you can see that you can click on these different icons to start browsing the different data sets. Let me start by just showing you what I did a couple of days ago when I found the data. I typed in fire incidents. And if you do that, you get a couple of a few different actually fire data sets. The first one I got interested in is actually the third one down, this one that says Fire Department Calls for Service. The reason I thought this was interesting is because it's last updated the night before, so I thought it'd be interesting to look at this data. So if you click on this, you then get this like UI that will in a second show you the table, and this table has like 30 columns. You can get a quick glance at what this data looks like. There's like a call number, an incident number for the 911 call, a call type, and there's all these like timestamps here for the exact time the call came in, and zip code of the incident. And finally, on the far right here, it says the neighborhood district that the call came in from. Okay, so this data you can download to your computer. So don't do what I'm about to show you, because I've already put this 1.6 gigabyte file on S3. So you don't want to download this and kind of saturate our Wi-Fi. But I'll show you what I did do 2 days ago. I clicked on export up here, and then I just basically clicked on the CSV file, downloaded the 1.6 gigabyte file, dumped it on S3, and that's kind of where we're going to pick up in a second. You'll notice here you can actually also get like JSON versions of this data. So that's kind of what I did. Okay, so I'm hoping that everyone has successfully logged into Databricks. If you're viewing this on the internet later on, then the way you can check out this data and follow along with this lecture is go to databricks.com/try, and then you're going to want to go to Community Edition on the right here. And this is basically going to give you a free sign up for Databricks. There's no credit card required. And the main reason we like to use this platform for talks like this is because there's no setup involved on your laptop, right? This is a Apache Spark cluster running in the Amazon cloud, and all you need to do the hands-on workshop today is Chrome or Firefox. So like Internet Explorer is not as tested, and Safari might work, but I highly recommend using Chrome or Firefox. Sign up for this. You should get an email within about 2 minutes. Log into your email and click on the link to get to Databricks Community Edition. Once you do that, by the way, please also write down these two links, bit.ly or bit.ly/sfopenlabs and bit.ly sfopenreadalong. Go ahead and download those two as well. And this down here, community.cloud.databricks.com, is the actual login to Databricks. But your email will probably have that link as well. So this file is about 1 megabyte file, the Open Labs file. This is the file that has our actual code for today. Okay, so I'm going to just continue, but if you are having trouble logging in, raise your hand. No one. Amazing. Okay. By the way, throughout the next 30, 45 minutes, just raise your hand if you have any trouble with anything. There are several people here from Databricks who can help. So what I'm going to do is I'm going to log into my own Databricks account. And I'll walk you through what you'll have to do to get to the environment. When you log into Databricks, this is what you'll see. The first thing you'll want to do is click on clusters down here. And let's go ahead and launch a Apache Spark 2.0 cluster. So I'm going to click on Create Cluster. I'll call this one Samir Demo. And I'm going to change the default from Spark 1.6 to all the way at the bottom, Spark 2.0, which has not been released officially yet, but it's in release candidate 2, and it should be released very soon. All the code I'm going to show you in this demo is going to be the new Spark 2.0 API. Okay, this is all I'm going to do. I'm just going to click on Create Cluster now. Okay, so this is pending, and it's provisioning a Spot instance in Amazon for me. While that's going on, I'm not going to wait. I'm just going to click on Workspace here. And I'm going to right-click on this white space. And I won't go to Create. I'll go to Import instead, because I want to import that 1 megabyte lab document or file. OK, so click on Import, and then just leave that on File. Click this button. And that is the Databricks cloud file, the .dbc file that is the labs file. It's 100 kilobytes. Now, the way you get that file one more time is this top link, labs file. That will give you that 100 kilobyte file. This read-along is basically a static HTML copy of the exact same notebook. If you are having trouble logging in, or you kind of just want to browse through what I'm doing and not really type any code, then feel free to do the read-along, and you'll just get a static HTML copy of the notebook. All right, but everybody really, I hope everybody actually uses the labs file and starts playing with this code. OK, so that's my labs file, so let me import it. OK, I guess my cluster is having a bit of a trouble coming up. Let me refresh this. OK, there we go. My cluster is up perfectly. I don't have to go to my backup environment. So you have to first make sure that you get this green button here that says running, or the green icon. That took about 1 minute for me. So I'm now actually ready to import my, my file one more time. So I'll click on Import and just click on that 100 kilobyte file one more time. And I'm good to go. I have this folder now here called SF Meetup. Once again, I right-clicked on this, and I went to Import, and I brought in my file. There are a few different notebooks here. So first, go to the datasets mount notebook, and then up here, click on Detached. Attach it to your cluster. I'll attach it to my demo cluster. And then put your cursor in this first cell and hit Shift-Enter to run that cell. And then move to this next cell and hit Shift-Enter on the keyboard. And those two cells should execute. And finally, if you run this last cell, you should successfully see a bunch of mount points showing up. One of those mount points you'll notice is SF Open Data. All right, so all I did is I just attached to my cluster up here, and I ran the 3 cells. OK, then we'll click back on Workspace on the left. And now what I'm going to do is see this little gray part here. I'm going to expand this column so I can see that there's actually 2 notebooks here, RunMe and README. README is a static notebook with all the cells already run. It's not what I would recommend doing. I recommend going to RunMe. In RunMe, the code is there, but the cells are not executed. So everyone should just go ahead and mount the data sets and jump into the RunMe version of the notebook, and then we can finally get into the material. OK, so what I'll do next is in the run me version of the notebook. I'll let it load for a second, and once it's done loading, I'm going to click on this detach button and attach it to my cluster one more time. It says attached. I'm good to go. Who needs help because they're not here yet? Just raise your hand and leave it up for a few seconds. Okay, there's a few TAs who will start walking around. I'll ask you to do that again in like 5 more minutes. Also, consider just asking your peer to the left or right to help you out. Okay, if you click on this very first cell here where you see the Spark logo, double-click on that and notice that this is actually a markdown cell. Let me make this a little bigger so the people in the back can read. Basically, all I did is I double-clicked on this cell, the first cell, and I'm just pointing out that that's a markdown cell that is pointing to 2 PNG files. And all these text files here are actually markdown files, or these text cells. To make you a little familiar with this interface, see like when you hover between the 2 cells, I can hit this plus button, and a new cell opens up if you hit the plus button. And then you can like write Python code in here, like 1 + 1, for example, and run the cell. You can also delete a cell like this by hitting this X. And you can click on the keyboard icon button up here to see operating system specific shortcuts. The only 2 important shortcuts for now that I want you to know are if I like make a couple of cells here, like x = 5, and then I make another cell here. Let me make this bigger. I'll make another cell here that says like x + 1. Okay. Here's the most important 2 keyboard shortcuts. If I move my cursor in this cell, in Windows, I can hit Shift-Enter, or in Mac, and notice that it runs the cell and moves the cursor to the next cell. Sometimes you're going to want to keep the cursor in this cell and keep running it over and over and over again without moving the cursor. For that on Windows, I can do Control-Enter. So see, if I run Control-Enter, the cursor stays there, and it's not moving to the next cell. And sometimes I'm going to want to use that technique. If you're on Mac, you can figure out the keyboard shortcut by just clicking on the keyboard shortcut area up here. If you come from a Jupyter or IPython notebook background, there is no command mode here. So you can't like hit escape and get keyboard shortcuts. There's really only one mode, and those shortcuts in that one mode can be run if you run any of these shortcuts right now. Okay, let me set the stage for what we're going to do. We will look at some of the 4th of July data for the firefighters' incoming calls to 911. Okay, so really quick, a little bit of information about Spark. As Jules was saying, it started at UC Berkeley's AMP lab in 2009. It's open source under Apache. The latest major stable release is indeed 1.6, but we're going to work on a preview release of 2.0 today. Most of the lines of code in Spark are written in Scala, but there is a Python API as well. Okay, so there's many different libraries in Spark. We will focus almost exclusively today on SQL and DataFrames, but there is a machine learning API, a streaming API, and a graph API. However, the SQL and DataFrames API is really the foundation and the gateway to get into any of these other APIs. So I hope you get a really solid foundation about what you can do with Spark that will let you build upon doing supervised and unsupervised machine learning, graph processing like nodes and vertices, and PageRank and shortest path, and also streaming. The way streaming works is pretty cool, by the way. In 2.0, what you do is when you turn on structured streaming in 2.0, you basically start building an infinite data frame so that your data frame or SQL query that you learn to use and write today will just translate automatically into structured streaming, and that infinite data frame, you can apply your code right away to streaming, basically. Okay. So if you're new to Spark, here's like Spark 101, a little bit more technical. There are many data sources you can read from. Basically, every major file system or database in 2016 you can read from. Spark runs in almost every major environment. Docker, EC2, Mesos, Kubernetes, Yarn. We will run exclusively in Amazon EC2 today, and we're going to be reading data from S3. The data we'll be reading is CSV data or Parquet data. All right, one more thing. If you're new to Spark, please don't use the RDD API. That's kind of like the internal API to Spark now. It's kind of older. You want to stick with this new API up here, DataFrame SQL and datasets. So here's what a Spark cluster looks like. A distributed Spark cluster has a bunch of JVMs. There's a driver JVM and a bunch of executor JVMs. You can have hundreds of executor JVMs, but you'll always have just one driver JVM. The driver JVM is kind of like the head of your Spark cluster. It does scheduling, and if you actually look at this, every executor here is running slots. And you'll notice that in this example, there's 2 slots on every executor. So what the driver does is the driver schedules tasks to run on the empty slots. Right? So the driver has a scheduler in it. It basically takes your code from the notebook and it schedules it to run in a distributed cluster. However, that is not what we're going to be doing today. We're going to be using Spark in local mode today. Local mode Spark is used for prototyping and learning the Spark API. This is what we're actually running right now. Your notebook, meaning this notebook I'm looking at right now, is connected to an EC2 machine in Amazon in which there is a 6 gigabyte container within which there is a 3.7 gigabyte JVM. Now, this special JVM actually has instantiated the code for the driver and the executor classes. So we've basically collapsed the driver and the executor in one JVM. And this JVM has 3 slots. We'll come back to like why this is important later, but essentially what that means is you can run 3 tasks at a time. If for whatever reason you need to run 6 tasks, that's doable. You can run 6 tasks, but you're going to have to do 3 and then 3 more. All right, so that's going to come into play in a little bit when we have to kind of re-architect a few things for performance. So I work at Databricks, the company created by the founders of Spark. One fact I'll tell you about Databricks is that in 2015, the engineering team at Databricks contributed 10 times more source code to Spark than any other organization. Okay, so let's get to our analysis. If you put your cursor in this cell and hit Control-Enter or Shift-Enter, I'll hit Control-Enter here because I don't want to move the cursor. Notice what I'm doing is I'm running the file system magic command in Databricks, and I'm listing the contents of this directory. And I see a CSV file in here. This is a CSV file I exported yesterday. And this file is a 1.6 gigabyte file. This is the file that we want to analyze initially with Spark. So what we'll do is we'll use the Spark object. This is a new object that came into existence only in Spark 2.0. So basically, if you just like type in Spark in a cell and hit Control-Enter, or just move to the cell and hit Control-Enter, you'll see that this is a handle for a Spark session. The handle for all functionality in Spark. Basically, this is the handle to get into Spark streaming, machine learning, SQL, DataFrames, and graph processing. So this is what we'll do next. We're going to use the Spark object to read the CSV file at that path I just showed you. And what I'm going to say here is a couple more extra parameters. There is a header in the file, so header true. And I want Spark to infer the schema. You saw how many columns there are. Like, I don't want to be defining all the columns manually. So I'm going to take a gamble and see if Spark can figure out the data types for all the columns. All right, so put your cursor in here and go ahead and do Control-Enter or Shift-Enter. So what Spark is doing now is actually kicking off a job that is doing a read of the data, and it's sampling some of the rows and columns to infer the data types. And now, if you do this, infer schema against terabytes of data, this will do pretty much a full scan of all your data, which is maybe not optimal if that's going to take like 20 minutes, right? So I'm going to show you a different technique. Notice this took about 28 seconds or so to go through like 1.6 gigabyte of a CSV file. So before I even do anything with this data frame, this fire service calls data frame, before I do anything with it, I'll show you the alternative approach of how to do this. So you can import a bunch of PySpark or Python Spark specific data types. And then here I've defined my schema manually. Notice that for every column here, I'm just basically giving it either a string type or an integer type. And I'm saying that all of these columns can be null. So true just means the column is nullable. Now, one thing I'll do is I'll go ahead and run this cell. It took only half a second to run. And then look at what I'm doing now. I'm still using the Spark object to read the CSV file. But this time, I'm saying schema is my fire schema from above. Notice if I run this cell, there's no Spark job that kicked off. It just used the schema I gave it. There is one more reason I'm doing this. So another reason I'm actually manually putting in schema is because this data, if you actually go to the city of San Francisco's data on the website, and if you look at the column names, they have spaces in them. So the column names have spaces in here like this, and this will cause problems with Spark. So I am bypassing all those problems by giving it a manual schema and removing all the spaces. Those are two things you should know. So let's just continue on with our data analysis. Okay, now I have this data frame from my static schema. Very often, what I like to do when I have a data frame is just look at the first few records in it. What I'm doing here is on the data frame, I'm limiting it to 5 rows, and then passing that into the display function in Databricks to create a HTML table of the data, and here I see it. I do see that the column names don't have spaces in it. That's pretty good. And yeah, I mean, the data looks fine. It's all there. There's a lot of columns, actually. But that looks kind of similar to what I saw on the internet, on the website earlier. OK, my data frame did load the data successfully. On my data frame, I can call the columns method just to print out all the columns. This gives you like a Python list back. OK, next. I like to always run count. I like to do it for 2 reasons. One, to understand how many rows are in my data frame, meaning how many lines were in the CSV file. Also, I like to run count because count does a full scan of the data, which means that my JVM is having to read 1.6 gigabytes of the CSV file remotely from S3. So this gives me just a sense of how long a full scan is going to take. Before I start doing complicated SQL queries, just a simple scan for benchmarking reasons, 20 seconds. Okay, so that sets the stage. The simplest full scan against S3 is 20 seconds. I have 4 million or so, a little more than 4 million rows in my data frame. Okay, cool. Go ahead and open up these Spark 2.0 documentation if you'd like to. So just right-click on these, go to new link. We usually don't give these links out often because they're kind of preview documents. But if you go to that first link and then click on the very bottom link here, you'll see that this will give you access to the Spark 2.0 documentation. I basically just opened up this first link here in a new tab, and I see Spark 2.0 here. Then go to Programming Guides and see this right here, DataFrames, Datasets, and SQL. This is going to be your source of truth for the API, so click on that. And then, there's a lot of stuff here. Just keep this tab open. And maybe we'll come back to this when we need to refer to something. Another thing to do is go to API docs here and right-click on Python and open this up as well. All right, this gives you access to the full API methods of PySpark. So just those are the 2 main things you need to have open right now. OK, I have my documents open. I'm ready to start doing some data frame queries. There are 2 fundamental operations in Spark, transformations and actions. here's an example of some transformations, like select to pull out just a few columns out of my 30 columns. You can do distinct, group by, sum, order by. Transformations essentially take the first data frame and give you a new data frame back. So that's what transformations are doing. They just basically take a data frame, modify it in some way, give you a new data frame back. All right? Actions are used to print results. Transformations are lazy. Actions trigger computation to happen. Let me show you what I mean by that. So the first question we'll answer is, how many different types of calls were made to the fire department of San Francisco? So on my data frame, I can call the select transformation, yank out just the call type column, and then call this action show 5. Select is a transformation and show is an action. And if I run this cell, I should see an ASCII printout of 5 of the first call types. Now notice something, okay? If I remove my action here, I'm deleting the dot show, okay? If I delete that, look at what's going to happen. See the Spark job that I ran earlier? Well, if you just call transformations, no Spark jobs run. In order to trigger any computation to happen, you have to call an action like show, and then that triggers the DAG, or basically the graph of all the previous transformations to run. Okay, so it looks like those are some of the reasons people call the San Francisco Fire Department. But I want to understand all the reasons. So I'm going to call 2 different transformations. First, out of all 4 million rows, select out the call type for every row. So this gives me that gives me 4 million specific call types. But sometimes there's duplicates, so I want to get rid of those and call the distinct transformation. And then I'm going to call show, and I actually know that there's actually 35 specific types of call types. So that's why I'm passing in show 35. And the reason I'm passing in false is because sometimes the call type is pretty long of a string, and I don't want to truncate it. So let me show you the results, and you'll see what this means. 35 means show me 35 results, 35 rows, and false just means keep the width here as long as the longest item in here. Okay, so these are the reasons people called the city of San Francisco. Okay, but what I really want to know is which one of these call types gets the most calls, right? Like this is kind of cool, but I want to get a count for each one of these call types. So that's what I'm doing here. I'm calling a few more transformations actually. I call select, then I want to group by the call type, one of the 35, then I want to count how many are in that group, and then order by the count in ascending order, false, so descending order. And finally, I should get like my first interesting insight. Why are the people of San Francisco, the residents here, or tourists, calling the city of San Francisco's fire department? Any guesses? My roommate in Florida is actually a firefighter, so I knew it would be medical incidents. This is by far the main reason firefighters get called. You can see here, it's about 2.5 million times it happened. This is massive. We have 4 million rows. 2.5 of them refer to medical incidents. And then 500,000 are for structural fires, alarms, traffic collisions were 158,000. Other citizen assist, outside fire, administrative. It drops pretty severely. Now, one thing is that, actually, I'll get back to the graphing in a second. Let's just continue. I do want to point out this, though. Notice it took 14 seconds to run that query. Right? This query right here, to do all of these transformations, took 14 seconds. In a little bit, we will learn how to cache data into memory so that this will become like 50 times faster. But let's hold off on that for a second. Another thing I want to do before we take a break is I want to do some time and data analysis. So recall that my DataFrame schema only has strings and integers, and this is problematic because these columns are actually timestamps. But when I provided the schema, I just said it was a string because it's easiest to load the data that way. But let me show you how you would cast the columns that are actually incorrectly labeled as strings right now into timestamps so you can do time-based queries. And then we'll take a short break. OK, so you can look at the Unix timestamp docs here if you're interested. But here's the gist of it. You basically are going to do some imports to get basically the Unix timestamp function. And then let me just scroll up really quickly and remind you what this data looks like. There's two different types of timestamps I've noticed. There's this type of timestamp, which is really just a date. It's month, day, and year. And then there's two columns like that. And then the other pattern that I noticed is like this. It's the month, day, year, and then this full timestamp and AM, PM. And you see all of these timestamps are actually like that. There's two patterns. I need to convert all these strings into timestamps. So that is what I'm doing down here. I kind of already gave you the code so you can quickly just review it. Here's the two patterns. That's the first pattern, remember? And this is the second pattern. What I'm going to do is, for all these columns, like this one, I'm going to say that this was of type pattern 1, casted to timestamp. This was of type pattern 2, casted to timestamp. And then make a new column that is the same column name, but then just put TS at the end of it, and then drop the old column. All right, that's what I'm doing. For like the 7 timestamp type of columns, I'm just casting it to an actual timestamp, then I'm dropping the old column. And I'm calling this new derived column the exact same name, but with a TS at the end of it. All right, that's all I'm doing. It's a simple cast. OK, so let me run this cell. And next, on this new data frame that now I tacked on CTS in there, on this new data frame name, let me print schema, and I'm hoping I'll see timestamp now. If I scroll down, actually, did that happen? Lower down. Oh, yeah, all the timestamp columns are at the bottom, actually. So there they are. OK. You can also just do a limit 5 and display the data frame, this new data frame that it has TS in its name. You can do that here as well. And the main way you can know that this transformation happened is if you go all the way to the end where the timestamps are. Notice how they show up differently now. So it's just like it's formatted differently, and that's a clue that the conversion and the cast did happen. OK, so what will I want to do with this now? Let's run a couple of cells, and we'll take a quick 10-minute break. On this new data frame alias, I'm going to select out the year from the call date column. There's a column that basically has the date the call came in. It's just month, year, date. From that, I'm going to use the year function to pull out just the year, like 2014 or 2015 from that. I want to know distinctly, like, how many years of data do I have? So, for all the 4 million rows, let's do distinct on that, and then order by year and show. So how many years of data am I looking at? Notice this is starting to take a bit of time to run now. If I expand this, you'll notice that it's kicking off like a Spark job 18 with 2 stages. And it's like running 3 tasks right now. And let's go and minimize this, because I'm going to explain what's going on here behind the scenes after the break. I just want to introduce you to the API right now without getting into the internals. Well, it looks like I have data from 2000 until about 2016. So 16 years of data. So in 16 years, about 4 million calls came in to the firefighters of San Francisco. And as I start doing more and more complicated queries, my query time is going up, which is a little alarming. Now it's taking 25 seconds to run this query. So I definitely want to start using cache in a little bit and start moving things to memory. All right, one last thing, and we'll take a break. How many service calls were logged in just the last 7 days? July 6th, which is today, is the 187th day of the year. So I basically want to know everything above day 180. All right, so just skim through this code. In my data frame, I'm going to filter down for year 2016, then do another filter for keep only the data where the day of year is greater than 180, because 180 is basically 7 days ago, day 180 of the year. And then look at what I'm doing. I'm selecting out the call date column. However, from that, I'm deriving the day of year. So I'm actually getting the day of year, which is going to be like 180 or 181 or 182. I'm getting that, and then I'm getting that distinctly, and then ordering by day of year. Let's run that and just look at what comes back. Once again, it's running a Spark job. Show is my action, and everything before this are transformations. Filters are transformation, select is a transformation, distinct and order by are all transformations. Okay, I do have 7 days of data here. 180 to 186, these days were found in the data set. That took 25 seconds to run. Look at this, if I get rid of the show, this just like doesn't do anything. It comes back in a tenth of a second or something. You have to call an action before computation happens. Okay, let's run this. Was this the same exact cell? Oh, this is doing a count now. So we're doing something similar. We're filtering out for 2016, filter out for just the last 7 days, and then count how many calls came in each of the last 7 days, and then order by the day of year. This should tell us, this should give us 2 columns. It should give us on the left a column for the day of year, like 180, 182, 183. We should get 7 of those rows. And then the second column should give us a count of how many calls came in on that day. By the way, July 4th was the 185th day of the year. And I was curious to see if there would be a spike. The spike actually happened after midnight. There were 1,000 calls roughly that happened on July 5th. And I'm assuming that's because of partying that was probably going on. Okay, last thing before a break is if you run this cell right here, it's basically the same code as up there, except I've wrapped it in display, and this is going to give me a bar chart, which is going to make it a little bit easier for me to visualize the last 7 days of call records to see if there was a spike on a specific day. So notice what I did here is basically I took this exact same code, but I got rid of the show. Okay, I took this exact same code, I copied and pasted it, but I deleted the show, and I replaced the, actually I just deleted the show, that's it. And then I wrapped the whole thing in display. And then you get back this bar graph, and this is showing me the days, day 180, 181, 182, and then it shows me how many calls came in on that day. By the way, you can see the table representation of this by clicking on the table on the left. See this table icon? You can click on that and just see the table representation, or click on this and do another visualization. Like, I don't know, pie chart doesn't really make sense, but it's pretty, I guess. Or you can go to bar. And then you can expand it out by dragging this over. So this is built-in Databricks visualization. And we'll take a break before we continue with the next section, where we'll take a 10-minute break in just a minute. But I do want to warn you that if you came here to kind of understand what happens with Spark behind the scenes, how to do optimizations, how to use the Spark interface to really understand what's going on, that's what I'll do right after the break. But before that, I'll leave you with one more thing as far as visualizations go. If you go here to Workspace, and then go to Databricks Guide on the left, Databricks Guide is a manual to Apache Spark and Databricks. 90% of what's in here is just about Apache Spark. And then maybe like 5 or 10% of this is some specific stuff about the implementation of Spark that we have at Databricks. What I wanted to show you here is I'm going to scroll down to visualizations. We're not going to have much time to do fancy visualizations today. However, maybe I want to do a D3 visualization. So I'm going to click on D3 on the left. And then if I scroll down here, notice that you can actually do display HTML and embed any JavaScript-based visualization library that you want. Basically, Databricks supports like D3, Matplotlib, Google visualization like Google Charts, Seaborn, anything JavaScript-based. Notice at the very bottom of this page is indeed a D3 visualization. You can see it's really just display HTML and then some HTML. But if I scroll down here, there's this. And if I move around, it looks cool. I don't really know what this is, but it's a D3 visualization. Now, you can bring this notebook and make this notebook come alive. I can't edit this code right now. Like, I can't click on this. It's kind of annoying. But what I can do is I can click import up here. I can do this for any notebook in Databricks Guide, and I can just like say, I want to import that to my workspace here, click clone, and then in my workspace, there we go. Now this notebook is in the root of my workspace here. And now what I can do is pretty cool. I can actually attach this to my cluster, and now I can run all these cells, and I can start messing around with that D3 visualization. I can like run this one, and you can do this for all the 200 or 300 notebooks in Databricks Guide. And that will be a really awesome way for you to continue learning Spark. Here's where I'm going to like kind of go a little bit deeper around what's going on behind the scenes. If this section is a little bit too fast, then there's going to be a YouTube recording of this, and the link will be posted in a couple of days on the meetup.com page. So basically, just feel free to just even watch me do this as a demo if it's like hard to keep up for some reason. You can review the recording later. Another question that came up during the break is, does Databricks Community Edition like just run forever for free? What we do is actually we terminate that cluster that you launched after 1 hour of inactivity. So that's how we keep this affordable and free for everyone. All right, so you can run as long as you need to, but if it's inactivity for an hour, it'll self-terminate. Okay, to get back to the notebook I was in, what I'm going to do is on the left, I'm going to click on Recent, and I'm going to go to the Fire Incidents Exploration notebook. And I see it's still connected to my cluster. And just to like refresh your memory on what we did so far, we learned a little bit about Spark. We learned that this is like what a distributed Spark cluster looks like with many different executors running on many slave machines in a data center. But I did clarify that that's not what we're using right now. We're using this local mode type of Spark cluster, which is for prototyping purposes. It's a 3.7 gigabyte JVM, and on this EC2 machine, there's actually about 10 different containers running, and perhaps 9 other peers from this workshop are also on the same EC2 machine as you, but in isolated containers. So basically what we did so far is we did a directory listing on S3 to just look at that CSV file. I pointed out the Spark session object, and that Spark object is what we used to read the same CSV file. And we said that the header is true, and then we tried to infer schema initially, and noticed that it took like 25 seconds, and we got the data frame back, but it had to do a scan, and the infer schema also brings in the column names the way they are in the file with spaces in them, and I don't want that because that's going to cause problems later on, like when I try to save a Parquet file. So for those two reasons, because of the fact of infer schema taking too long to run for the full scan, and I want to manually give my column names without spaces, for those two reasons, I then showed you how you can actually provide schema yourself manually. This is basically me manually making a schema type. I can name these columns whatever I want, and I just named them very similar to the file, except I removed all spaces. And I only use string and integer types here. Actually, I used a Boolean type down here also. Okay, so then I provided a schema manually, and I noticed that this time around, when I made the data frame, it did not run a job at all because I already knew the schema. I didn't have to infer the schema. And then I, started looking at the data frame, limit 5 rows, look at the columns, count 20 seconds to read all the data, and it's 4 million rows. There's transformations and actions in the DataFrame API, but in just a second, I'll unlock the SQL API. So if you're more comfortable with that, I'll show you how you can run SQL queries if you don't want to use the DataFrame API. The DataFrame API in Spark tries to be as close to the Pandas DataFrame API as possible. So if you're comfortable with that, you'll find the DataFrames API very, very natural. However, in Pandas DataFrames, if you call a transformation, that is eager. It happens right away. The computation happens as soon as you call a transformation. In Spark, transformations are lazy, so they just get build up until you call an action. And the action will collapse a bunch of transformations and do a bunch of optimizations and then run your computation. So that's the main way Pandas DataFrames are different from Spark DataFrames. This is the first implementation of DataFrames that are lazy, meaning you can tack on 100 transformations and nothing will happen until you call an action to look at results. And then it will figure out the most efficient way to run all those 100 transformations. Okay, and then we started looking at the call type. This is one of the columns we were looking at. We noticed that there's 35 different types of call. Most of them are medical. If this date time part was confusing to you, then really all you need to remember is that the original data frame had a whole bunch of strings for columns that were actually, time or date. So what I was doing here in this is I'm just defining these two patterns and then applying them to convert those column types from string to timestamp. And I don't want to cover this in depth. This is just some sample code I wanted to show you for how to do that. And then now I see that these last few columns show up as timestamp, which then unlocks essentially the ability to do this year. This would not have worked before. I'll prove that to you by removing, actually I deleted the old column, didn't I? If I run this on the earlier data frame, this would not work because this year function only works when the column type has a timestamp in it. If this was a string, this year function wouldn't work on that column type at all. This is a timestamp column type, therefore I can apply the year function. I pull out the year for every row, then I call distinct to just keep the years distinctly, and then order by this column, this derived column, order by the year column. Okay, let's just jump on to the next section. Memory and caching. Notice those earlier queries were taking 20 seconds. Okay, here's where things get a little bit interesting. On my data frame, the last data frame that has the correctly defined timestamp columns, I'm going to convert that data frame to an RDD and get the number of partitions, and I'll see that it's 13. So what does this mean? Well, internally in Spark, data frames are made of partitions. Here's a visual way of thinking about it. My data frame, fire service calls timestamp data frame, is made of 13 partitions. So basically, a 13th of the data is in each partition. The reason this is all dashed is because technically this data frame doesn't exist in memory. This is just an idea of a data frame. If I try to do something with this data frame like a count action, or on this idea of a data frame, if I call 5 transformations and then an action, then Spark actually starts reading the first CSV file from disk on S3, and it then materializes this data frame for some period of time, and then immediately transforms this data frame in memory into 3 or 4 or 5 other data frames, depending on how many transformations I'm doing. But here's the thing, 13 is not optimal. If you really want to know how to use Spark correctly, you will not go with this default of 13. Instead, recall from way earlier, the type of cluster that you're running right now is actually a local mode cluster, this one, right? And it has 3 slots. You can run up to 3 tasks simultaneously. So the thing with Spark is that you can go pretty far by just learning the API. That's what we did so far. However, if you start aligning your knowledge of the Spark API to the actual cluster architecture, you can get better performance, and I'll show you how. Ideally, if I have 3 slots, then maybe I want a data frame in memory that is some multiple of 3, like maybe 6 or 9 or 12. But I definitely don't want a data frame in memory that's going to be 1 partition. Because if I do that, the other 2 slots are going to remain empty. So I'm going to actually take the data frame idea, the data frame idea that says 13 partitions. I'm going to repartition that into 6. And then I'm going to cache the data frame with 6 partitions into memory permanently. And then I'm going to start operating on that data frame in memory. So let me show you how to do that. Sorry, let me just scroll back down to where I was. OK, this is my data frame right here with 13 partitions. I'll repartition it to 6. And then I'm going to make a view for that called Fire Service View. OK, run that cell. And then I'm going to say, go ahead and cache the table. OK, before I run this cell, let me show you something. I'm going to click this, and then go to this UI and open it up in a new tab. So if you've never seen the Spark UI, this is really important. Just kind of click this down arrow, right-click on this, and go to UI. Notice a whole new tab is loading. And there's going to be a lot of information overload for new people using Spark here. I will explain at least the fundamentals of what's going on here. But for now, all you really need to do is click on storage. And notice that it's empty. There is nothing showing up in storage because nothing is cached. Storage just shows you the data frames are cached in memory. And I didn't run the cache command yet, but I'll do it now. OK, so I'm going to run the cache command. Well, it ran in like 1/10 of a second. That's really suspicious because I know it takes 20 seconds to do a full scan of the file on disk. So it didn't even read the file. Because cache is lazy, it doesn't actually trigger the cache to happen until I do a subsequent operation like count that actually does need to read all of the data from disk. Now, this count is special because now it is going to do 2 things. It's going to actually read all the data from disk and tell me that there's 4 million rows in the file. But this count is going to take much more than 20 seconds to run because this time it's going to go ahead and materialize this cache as well. Actually, it's going to read the file from disk, get a data frame temporarily in memory with 13 partitions, then it will repartition that into 6, and then it will cache that in memory. So that's what's going on right now. And this is going to take like a minute or a minute and a half to run. If I expand Spark jobs right now, job 23 is running, and I can see that the first stage in job 23 is actually creating a data frame with 13 partitions. That just has to do with the way Spark reads from S3. It reads 64 megabytes of the CSV file at a time, and that basically ends up being about 13 partitions. But notice what's happening actually is as soon as it makes that data frame, it recreates a new data frame with 6 partitions, which is about to happen right now. There we go. Now that we're here, I will be able to come to storage, and I can probably in a second start seeing this data frame with 6 partitions materialize in memory right now in just a second. There we go. The first 3 partitions of 6, 50% have been materialized. It's taking up about 309 megabytes in memory. If I click storage one more time, it's not all done yet. There we go. Now it is. 6 of 6 partitions are in memory, 100%. It's taking up about 618 megabytes in memory. Granted, this is a 1.6 gigabyte file on disk. However, when you put a data frame in memory, Spark uses the tungsten binary format to columnar compress this data in memory. So the short of why this is 600 megabytes in memory is because we're doing columnar compression, And that makes the storage in memory be far more efficient than the serialized data on disk. And if I click on this right here, I can see how large each one of the 6 partitions is. See down here, each partition is 103 megabytes. So this is my representation of the data in memory. If I do anything with this data frame, it's going to require, in the first stage, 6 tasks, of which only 3 can run first on my 3 slots, then 3 more, and now I'm done analyzing the full data frame in memory. Okay. Also notice that if I actually have about 1.3 gigabytes of data remaining, that I can cache more. I can cache that much more data, essentially. Okay, let's go back to the notebook. Notice that took 100 seconds to run. What I'm going to do here is I'm going to pull out a data frame from this table so that now this data frame is operating on the memory cached version. See this name, Fire Service DF? Anytime you see this, it actually came from the cached version in memory. So what that means is if I do this, like on this new data frame name, if I call count, it'll run in like 1/10 of a second. And it's going to use 6 tasks. Well, first of all, look, it's like skipping the first stage completely because it doesn't need to read from disk, the CSV file in S3. It's instead reading directly from the representation of the 6 partitioned data frame in memory. So that's the stage it reads from, and then it actually launches this last stage here to do a count as well. Okay. Is my table cached? True, yes. This is basically what I have in memory right now. I have 6 partitions, each about 104 megabytes. Total data frame size, 626. Why did I use 6? I use 6 because I know that in general, when you're putting data frames in memory, the sweet spot that you should aim for is each partition should be 50 megabytes to 200 megabytes in memory. So don't have multi-kilobyte size partitions that are like tiny or multi-gigabyte size partitions that are large. Aim for something like 100 to 200 megabytes. That's why I went with 6 myself. And I already showed you this in the UI as well. Okay, one more thing. We did a whole bunch of work with our data frame, right? We read the CSV file, we converted a bunch of the columns from string to timestamp. And the thing is, if I'm like going to need to take a break and I want to go, stop doing some analysis for a minute, here's what I would actually want to do right now. I would want to take my data frame, write it down as a Parquet file to S3 so that in the future, if I want to continue my work, I'm going to read this Parquet file, which is going to give me a data frame with 6 partitions with all the columns properly formatted, like some of them will be timestamped. So this is a very common operation, right? We just did the whole loop of ETL. We did like extraction of the data from CSV, we transformed it, we cast some of the strings into timestamp, and now I'm going to load it into a Parquet file, and that's what I'm doing right now. I just basically say data frame, save it as Parquet. You can also save it as JSON or CSV, but Parquet is a very efficient format. And this is going to let me read the file way faster than CSV. Recall that there's no reduction in data, right? This is still 1.6 gigabytes of data fundamentally and 4 million rows. I'm writing all 4 million rows right now to this Parquet file in this temporary location on S3. And this should just take a second. It's running right now. And once that's done, I'm going to just run here ls here and show you what this Parquet file looks like. See how it has 6 different GZ compressed parts. So these are, what just happened is that data frame in memory with 6 partitions, each one of those 6 partitions just dumped down the GZ compressed version of that partition as an individual Parquet file. So in the future, imagine that like my cluster self-terminates in an hour. However, when I come back like tomorrow morning to continue doing data analysis, I can read that Parquet file into like a temporary data frame or something, And then I can get back to my data right away. And this Parquet file has in it embedded all the correct column names without spaces and all the correct data types like string, integer, Boolean, or timestamp. So now I want to point out one more really important thing. If I take this temp data frame, like check this out. I take this temp data frame, and what I'm going to do is open up a new cell, and I'm going to do a count on it, which does a full scan of the Parquet file on disk. I just want you to see how long it's going to take. In half a second. Parquet files are really efficient to read from. In Spark 2.0, there's actually a 3x improvement to the throughput of reading Parquet files from just January 2016. In January 2016, 6 months ago, Spark 1.6 was cutting edge. Since January of this year, there has been a 3x increase to reading Parquet files. So basically, I always want to take CSV or JSON that are non-optimal, do my ETL, write it back down to Parquet, and then from there, I'm going to start doing more sophisticated analysis. So let's do that in the last 10 or so minutes. First, SQL queries. Now that I have a view defined on my data frame in memory, you can just do like %SQL in Databricks. And this is a magic command. And it lets you run SQL queries. So you can do like select all from my table view, and there's 4 million rows. By the way, if you're running Spark on-premise, like on your local laptop, this %SQL will not work on Jupyter or Zeppelin or in the Python shell. You'll need to do something like, it's something like, Spark.SQL. I'm doing this off the top of my head. It's something like that, and then you do something like that, and I don't know if that will run. Maybe it will. Oh yeah, and then I want to do, oops. This gives me back a data frame, and then I'll do show on that. Oops. That also gives me back a data frame. That should run. Yeah, there we go. So that's how you run this, like if you're running in Jupyter. The %SQL is just a magic command for Databricks. Okay, let's do something a little cooler. Oh yeah, this is pretty cool because it's got colors in it. All right, so what happened up here when I did this count? Right, the way this looked earlier, recall, let me just get rid of this complexity. There we go. I just did a count. Now, if I expand this, it ran like 2 stages. The first stage was skipped. It ran stage 59 with 6 tasks, and then stage 60. Let me show you this in the Spark UI. So if I go to the UI up here, this was job 36, right? So let me go up here to, I need to click on jobs, and I need to find job 36. Oh, well, it happens to be the first one here. This is my job 36, and this is the job with 2 stages that ran, 59 and 60. So notice if I just kind of scroll a little bit to the right, on the same row, I can see that this kicked off 2 stages. A total of 7 tasks ran. So here's what I'm going to do. One thing here, one level of depth. I'm going to click on this link under the description column. When I do that, now it's going to show me more details about the 3 stages. The one that skipped is down here. It didn't run at all. These are the 2 that ran, 59 and then 60. Stage 59 is the first stage that ran. And notice this stage read 620 megabytes of data from memory. And then this stage used 6 tasks to do that. Basically, each task read the 103 megabyte partition of the 6 partitions. And then this stage emitted 350 bytes of data. What basically happened is these 6 tasks each wrote down a file to S3, and those 6 files in total amount to 354 bytes. Then stage 59 was completed, it finished, and then stage 69 ran, which launched only 1 task that read the shuffle data from before, so it read all 6 files, and then it gave me the results of the count. What actually happened here behind the scenes is if I drill deeper into stage 59 with 6 tasks, I'm going to click this link here to understand what each one of those 6 tasks did. Just scroll all the way to the bottom. Here are the 6 tasks, the task IDs. Notice each task read 100 megabytes of data, and then each of the 6 tasks wrote down one record that is 59 bytes to SSD. What basically is going on here is each one of these 6 tasks is reading the 100 megs of data and then doing a local aggregated count. Like this guy's going to say, I see 800 million rows. I see 750 million. That number, 800 million or 700 million, is being, or 700,000, is being written down here. So each partition is basically, or each task is just writing down how many rows it saw in its 103 megabyte partition. So just one number is being written down, and this number is going to be, if you actually open up that file on SSD, it's going to say something like 800,000 or 700,000. But the problem is we have 6 different files. Each file is giving a aggregated count of just its local partition, and we need to sum all the numbers up. All 6 of those numbers need to be summed up so we get the final count. That's exactly what's going on in the next stage. Stage 60 right here is running only one task, but that one task, notice all the way at the bottom here, it's hard to see if you're in the back, but this one task is reading 6 records. Those are the 6 files, and then all this guy does, it runs in 1 millisecond, because all he has to do is sum up 6 numbers, and then he says, I see 4.1 million or whatever rows. So that's a little bit about like what's going on behind the scenes, and this UI is the best way you can start diagnosing your performance and optimizations and debugging. This is like ground truth. And notice here, by the way, if I go back to the earlier stage, which had 6 tasks, see this one? I'm going to show you something kind of cool. See over here it says event timeline. If I expand that, this shows me the 6 tasks in stage 59, the first stage. And I'm not going to cover this in depth. I just want you to see that each one of these rectangles is a task. The first 3 tasks run first, and then as soon as a task completes, another task number 4 launches, then task 5 and task 6. Green is compute time of the task. Red is deserialization time, and blue is schedule or delay. These colors can be very useful in trying to figure out where the bottleneck might be in your Spark application. These 6 tasks all wrote down one file to SSD. However, it wrote it so fast. See up there the yellow for shuffle write time? You know, see this yellow right here for shuffle write time? Technically, you can't really see it, but the end of this, at the very end, is a tiny pixel of yellow because it did write something down, but it just happened so fast. If I was writing a lot of shuffle data, meaning there was no reduction in data, like I do something where there's the shuffle write has to still write all 1.6 gigabytes of data down across 6 tasks, then I would be seeing a lot of yellow here. Okay, that's it for this part. Let's go back to the code. All right, that's a little bit about behind the scenes, about how you can use the Spark UI. Next, I just want to do the SQL query. You guys all know SQL, so you can see that I'm doing some neighborhood analysis here. I'm basically saying, I want to know which neighborhood in SF generated the most calls in 2015. Any guesses? I had a guess before I did this. I'll be honest. I thought it would be the Tenderloin. You know, but let's see what happens. So I'm running a SQL query. I want to get a column for neighborhood district, and then another column for the count. And you know, I'm doing a where clause, keep only 2015 data, group by the neighborhood, order by the neighborhood count, in descending order, give me the top 15. Indeed, Tenderloin last year in 2015 had 40,000 calls to the fire department, and then south of Market, 30,000. And if you go to some of the other neighborhoods, it really drops, like Chinatown or Pacific Heights last year only made about 6,000 calls to the fire department. Okay, by the way, you know, we will understand in just a second. The last thing we're going to do is find out what type of calls the Tenderloin was making. So I thought that would be kind of cool to do. But one thing I want you to see here, see the Spark jobs right here? I'm going to expand that. And there is something weird here. Why does this say 200? Does anybody know? Raise your hand if you know what this means, 200. the senior director of training at Databricks knows, but that's cheating. I'm going to tell you something. You know, this query ran. It ran in like 2 seconds. But what happened actually is there is a static setting in Spark, and that setting is set to 200. What that setting means is it means that anytime a shuffle happens, how many partitions should be in the data frame after the shuffle? And unfortunately, that's hard set. 200 is not ideal for my data set. I want to change that to 6. I already told you why I like 6, because, you know, in this shuffle, by the way, there was no reduction of data. I went from a data frame in memory with 6 partitions to a data frame in memory with 200. Now, this is basically like the internals of Spark. I don't want to explain why this happened, but this did happen. And like here, if I click on this I right here, the I next to the 6, it's the shortcut to the UI. And if I go and look at the 6 tasks that ran, notice now that the shuffle right was about 3 kilobytes of data. The shuffle right was tiny. Each task wrote 42 files. So 6 times 42, right? 6 times 42, I think, should be like 200. 42 times 6 is 252. OK, 252. If I scroll down to the next task that ran, next stage, this stage with 200, what's going to happen here is, oh my God, there's in this stage 200 tasks ran. They read a tiny, tiny, tiny amount of data. It's actually like barely even showing up. This is non-optimal. I'm going to show you how to fix this. I basically never want a data frame in memory with 200 partitions. So here's what I do. See this setting here? It's set to 200. I'm going to change it to 6 and verify that it's set to 6. If you want to know more about this setting, copy this name and just go to the Spark documentation right here. Remember, I went here to DataFrames. Just go there, search for that, and it explains what that means. OK, so I set it to 200. The last time I ran that query, it took 1.2 seconds. This little tiny optimization, is it going to make it any better? Well, I don't know. Now it's running in 0.7 seconds. On big data, that would have been actually a significant speed increase. OK. By the way, there's like a bunch of SQL commands you can run. This is describing my table. OK, we're almost done with the day. I want to explain one more thing. There's a catalyst optimizer internally in Spark. And what it does is it takes your SQL query or your data frame query, generates a logical plan, which flows through this catalyst optimizer through logical optimizations and physical optimizations, and it finally generates some RDDs and runs that code. Now, I'm not going to have time to cover all of this today, but I am going to show you something. If you want to learn more about what's going on behind the scenes here, here's what you can do. Look, this is a SQL query, the same one as before. If I run a SQL query, it gives me back a data frame. OK? Just look at this code right here. Look at what I'm going to do next, though. I'm going to tack something on at the end here. I'm going to tack on explain true. If I run that, look at this. Now it's saying it didn't run any code. It's just showing me the parsed logical plan. And then it's showing me the analyzed logical plan. And then it's showing me the probably like other logical plans and physical plans. What are all of these? Here's the optimized logical plan. Well, this stuff right here is all the different phases of flowing through this catalyst optimizer. I'm only pointing this out because as you start learning more about Spark, this is what you're going to want to do to debug your code. And do this, and then post your question on the Spark mailing list and say, here's all my plans. It's not running, or it's running really slow. Then they'll be able to help you. One more thing that you can do to understand what's going on behind the scenes with this engine right here. See this SQL query right here? We ran it right here, right? It ran job. Which job was this one? I'm going to run this one more time. There, I just ran that. And now it ran job, what is this, 40? Job 40. Okay, so check this out. You can go to the Spark UI. I'm going to show you one new thing. Click on SQL up here. And notice that the top, here's job 40. Don't click on that. Just notice that this is the job 40 that I just ran. If you click on this, it shows you a visual representation of what just happened. To do this SQL query right here, this SQL query translates into this physical plan behind the scenes. It reads data from memory, and then it does a filter, it does a project, it does an aggregate. Exchange means shuffle. So it does a shuffle, and then it runs a whole other stage. All right, so hopefully this will help you down the line with your debugging. If you expand details here, it shows you the exact same logical plans and physical plan that explain true shows you. All right, so this is just a little bit of depth if you want to know more about what's going on behind the scenes. Okay, we're close to wrapping up and opening it up for Q&A. However, another really important thing that you would probably need to do if you're going to use Spark, there's all the stuff I already covered, is a join. This might be really important because, look, there's another data set I found yesterday. It was not fire service calls, but fire incidents. This was it had an incident number like this. And then the thing I liked about this different data set is if you scroll over here, it has this thing that says why somebody called 911. See the primary situation, like building fire or, I don't know, outside rubbish fire or overheated motor. This is interesting. I was wondering, why was the Tenderloin calling? And then perhaps why does a more richer part of San Francisco call? So that was the next thing I was wondering. So I basically loaded that file I just showed you into S3. Here it is. Let's load it up into a data frame called incidents data frame, okay? A totally different data set. I'm going to stick with infer schema here because it will be fine for my example. Let's print the schema here. This is the data. It doesn't translate the timestamp correctly, but that's fine. I don't need the timestamp. How many rows are in this data? I think it's 1 million. This file, these incidents are all non-medical related incidents. I think for privacy reasons, they don't track incidents here if it's medical. These are all non-medical incidents. Okay, and there's, in the incidents data frame, there's only 400,000 rows. It's way smaller than 4 million. Here's what it looks like. But that's not what I really want to do is a join on the incident number. Because my earlier data frame also had an incident number. I want to do a join on that. So notice when I made my data frame, I did something kind of tricky. I don't know if you noticed. I made my data frame, and then look at what I did. I said with column renamed, take the incident space number and rename that column to just incident number. Get rid of that space so that I can do the join. I kept all the other column names with the space in there. All right, so the join is super simple to do. Here it is, my fire service data frame that is currently in memory. And then I said join it on the incidents data frame on this column on both. And by the way, I also tacked on a cache at the end here so that when it reads the incidents data frame, it goes and caches that in memory as well. And then I will have both data frames in memory, making my join super efficient. So that's what I'm doing here. And I just basically called it join data frame to keep it simple. And then here's now my massive join data frame in memory with probably 60 columns. Here we go. It's actually now reading that second data frame because that was the first time it actually needed to do that. And here we go. This is my massive data frame. So now I've joined on the incident ID. And finally, I can do my query right here. Filter for only 2015 on my joined data frame. And also filter for the neighborhood district of Tenderloin. And how many do I even have? In 2015, 8,000 times somebody called. 8,600 from the Tenderloin. And here we go. What was the reason? So here I'm grouping by primary reason. and I found this interesting, false alarm. Most of the calls were false alarm, about 10% of the data, the calls. And then there were like malicious fire alarms. That doesn't sound very good. Like, unintentional fire alarms. Oh my God, alarm system sounded due to malfunction. A service call. Not all of these would probably annoy a firefighter. So my theory is that firefighters probably don't like going to Tenderloin. But let's go to one of the other districts. Like, let's go up here to like one of those districts that only called like 6,000 times, right here. I don't know, what's like a district with Pacific Heights? Is that like a rich one? Let's try that one. They called 6,000 times. What type of calls came out of the Pacific district? I'm just going to go back to the same query and replace the string Tenderloin with Pacific Heights. How many times did they call? For non-medical reasons, 2,000 times. Let's go ahead and see why. So Pacific Heights called, okay, also false alarm, but only 6,000 times for that. Smoke detector, building fire. That's pretty legit, I guess. So, okay, so you can kind of play around with this and continue this analysis. Oh yeah, I did Russian Hill. These guys were actually pretty good users of their local 911 service. Main reason they called from Russian Hill is to do service call. There's fake call, false alarm. So okay, I thought that was kind of interesting. We did a join. Another thing, I just figured I'd show you that you can actually import pandas here and take your joined data frame. This is a Spark data frame. Filter it down just to 2016, so it's tiny now. You can actually convert it to a pandas data frame. And now this pandas 2016 DF is a Python pandas data frame. So, if you want to do something in pandas because it's a richer API and there's some trick in there you want to use, then this is an example of just doing some stuff. None of these are Spark operations. These are just pandas data frame operations. And that's it. I'll open it up for Q&A for the last few minutes, but I want to say one more thing about where you can go with this. Here's where I recommend, here's like what I would do next, right? What I was thinking about doing if I had more time was using the ML library here, the machine learning library, to do decision trees. I thought that would be kind of cool. One of the columns I noticed in the join data frame says whether or not the call was for a life-threatening emergency. And that's a Boolean. You can just set that to true or false. And I thought it would be interesting to then integrate Spark's decision tree from the ML package and train it on all the data except for 2016. Keep that for testing data. And try to see if you can train a model to use these 60 or so columns to be able to predict with like hopefully 95% accuracy. So as soon as the call comes in, based on the timestamp of the call, the location of the call, and what was going on, at that time, you should be able to then predict whether or not that would be a life-threatening call. And if it is a life-threatening call, you might take that a little bit more seriously. And based on your metrics, alert the fire department that this is probably not a fake call. Even if it's in the Tenderloin, our metrics are telling us with 70% probability that this is a life-threatening call. I don't think that service exists, but I hope that somebody builds that. And I think that's some of the cool things you can do. Another thing you can do with streaming is if the fire department of San Francisco connects their incoming call station to Spark streaming, you can actually run some MLlib algorithms on the live stream, like logistic regression, linear regression, k-means clustering, and you can apply ML algorithms on the stream and start doing analysis on the stream of data coming in. So that's where I would basically go next with this data, and if you had more time, I would try to cover some of that. Okay, that's all I have for now. I'll go and open it for Q&A for the last 5 or 10 minutes. And I do have people from Databricks here who I might call up on stage if I don't know the answer. Cool.
Well, give a big hand to Samir, guys.
Thank you.
I know there was lots of information, but I think this is a great place to get started. You actually saw the power and potential of what the Databricks Community Edition can do, and all the information that today was parlayed to. You can actually go home and deal with it. Do you guys have any questions? Oh, one at the back. Okay, I'll go in this ascending order here.
So some of these things you can do in SQL, or you could do it with DataFrames. Is there? I mean, you showed the optimizer, or
You mean with Pandas DataFrames?
sorry, I'm talking Spark.
Oh, in Spark, you can do things with SQL or with DataFrames. You were saying.
Yeah, is there benefit to going one way or the other?
There's absolutely no benefit at all.
Really?
If you look at this, remember this like catalyst thing I showed you? This like at the very end. Notice something here, okay? Let me just scroll down to Catalyst. Right here somewhere. Yeah, right here. Here's something important. Regardless of whether you write your query as a SQL query or a DataFrame query or the newer datasets API, once it flows through Catalyst, the exact same physical plan will be generated and run as RDD code. So it doesn't matter. You just pick your API and whatever you're more comfortable with, and the exact same physical plan will come out. So it's not going to be any difference in performance.
And then with SQL, can it handle things like nested queries?
It should handle nested queries. Spark 2.0 supports the full Spark, the full SQL ANSI 2013 standard. So all of the SQL 2013 queries will run in Spark 2.0. This is kind of a milestone for the Spark project. Like Spark 1.6 could run a lot of queries, but not all of the SQL 2013 queries.
Actually, if you go to the Databricks blog site, we just released a nested subquery command, how actually Spark 2.0 does that. And it actually shows an explanation of how this query plan is executed. So you might want to try that. It's called subqueries in Apache Spark 2.0. Go to our engineering blog and you'll actually see that. And that's exactly what the question was about.
Spark 2.0 is kind of come of age. I think that it has finally become kind of a drop-in replacement for like Oracle or Hive queries. Your SQL query should translate pretty cleanly from other engines to Spark SQL. Any other questions?
Any other questions? Oh, there was one in the back.
Hi. Yeah, I'm curious to know if you wanted to basically chain together multiple notebooks into some kind of pipeline.
Yeah.
Is the best workflow for that simply writing to disk and then reading off of the disk?
In Databricks, we actually have a technique to do that. There are a lot of magic commands in these notebooks like %SQL, %FS. I didn't tell you though about %SH that lets you run like bash commands. I also didn't tell you about %run. If you do %run on a other notebook title, it will. If I go to the very top of this notebook and the first cell says %run my Databricks mount notebook, then if I run that cell, it will actually trigger the other notebook to run, which itself might be running many other notebooks that are getting triggered to run. And then what I can do in Databricks like Professional or Enterprise Edition is I can go to Jobs over here, and then I can actually take my final notebook and productionize it to run on a cron schedule like at midnight, and then that will basically just launch a cluster only for 1 or 2 hours, run my analysis, write the results back down to Parquet for the other downstream consumers of my data. Unfortunately, the Jobs feature is not turned on in Community Edition. It is in Professional Edition of Databricks, which costs $100 a month to start out with. And with the $100 a month, you can run as big of a Spark cluster as you want, unlimited size Spark clusters. However, you pay 40 cents per node. As of July 2016, if you're watching on YouTube, the prices will probably drop in the next few months. But essentially, you pay $100 a month, run unlimited Spark clusters. We just charge you like an hourly fee. It's a small fee on top of the EC2 cost. But I think it will save you a drastic amount of time as opposed to like running yourself in EMR or doing all the DevOps yourself. Any other questions? By the way, this is Apache Spark. You can export these notebooks as Scala or Python and run all this code yourself. let me just show you that. Like, we are very careful about not doing something like locking people into our platform. So here, you can click on this notebook we've been using and go to export and export it as a Jupyter or IPython notebook and just start using it on your laptop. Or you can export it as a .py file, as a source file. And so basically, you can prototype in Databricks, export it as a .py file, and then run that .py file in your production cluster because you can't get the data off of your data center. All right, so that might be kind of useful for you guys if, as you play around more with these environments.
Samir.
Yes.
John. Just to jump on the whole workflows thing, there's a notebook workflows that's coming out that basically allows you to do things in response to certain sort of like outputs from notebooks. And that's about to come out like in the next week. So yeah, you should check it out.
All right, let's take like 2 more questions, maybe max, and then I'll hang around here for a few more minutes if you guys have any questions. Recall that this is all on YouTube. I'm sorry if I moved a little bit too fast. But hopefully, you know, you'll be able to play around with this stuff later as well.
Going back to the, you know, this being the 2.0 and it's somewhat still being in beta, what is your kind of, I guess, your suggestion as to us working it if we want to work on something that's going to be going into production?
How much longer might you go into production from now?
Let's say like even like 2 to 3 months still.
I think if you're going to go into production 3 months from now, you should absolutely prototype on the release candidate 2 of Spark 2.0. There's a lot of reasons. First of all, Spark has been going through a complete re-architecture for the past 1.5 years. And that re-architecture finally comes to end with Spark 2.0. You basically want to build all your prototypes right now in 2016 on 2.0. So your API is going to be the new API of Spark that will remain stable for the next few years. If you write on 1.6, you might have to recode that in a few months to use the new 2.0 API. In addition to that, in 2.0, out of the box, your 1.6 Spark code will run about 10x faster. There's a lot of optimization, specifically with things like whole stage code generation and vectorization and binary formats in memory. There's a lot of interesting internal cutting-edge things that have come to fruition finally in 2.0. Reading Parquet files is 3 times faster than before. You want those optimizations, and you want all the bug fixes that went into, I think, 2.0. So I would recommend prototyping on 2.0 right now. Anything else?
And to
No?
Samir.
All right, guys.